Yes, I think it's on. Okay, so hello everyone, and welcome to the fifth seminar of the Beyond the Edge seminar series. My name is Bernardo, and I'm a PhD student here in the Beyond the Edge doctoral network. I specifically work in the Sentai Institute and the Politecnico di Torino in Italy. And today I have the pleasure to introduce you to the speaker, which is Dr. Thomas Varley, who is currently a postdoc at the University of Vermont in the US, and more specifically in the Vermont Complex Systems Institute. So just to give you a brief introduction of Dr. Thomas Varley, he holds a dual PhD in complex systems and in computational neuroscience from Indiana University, also in the US. And their research interests lie in the study of emergent properties of complex systems, with a particular emphasis on higher order interactions in the brain, and also the biological basis of neural computation, and of course, using a lot of tools from information theory, which we'll see in this talk. So, Dr. Valley, it's a pleasure having you here, and the floor is yours.
All right. Thank you guys for inviting me. I'm really looking forward to chatting with you guys. Um, that was a great introduction. So yeah, I'm coming to you from the Vermont Complex Systems Institute, and yeah, it's really exciting to get to talk to folks in Europe across the Atlantic. So today I'm going to be sort of introducing kind of an odd idea. This is something. Why is my thing not going forward? There we go. Um, this is sort of a this is less of a like, here's a bunch of new results, from experiments I ran kind of talk, and more of a conceptual thing. I want to introduce this idea that I have been sort of mulling over since I finished my PhD, and it's this idea of dark information. Okay, and so I'm calling this sort of the dark information hypothesis. And so I'm going to start by um, sort of giving you the 10,000 foot view of what this idea is, and then I will walk through the basics of classic Shannon information theory and then a little bit of multivariate information theory to try to build up some of the mathematical foundations required to really talk about this idea rigorously. And I know that this is a group that's already familiar with sort of general theories of higher order interactions. Um, I don't know how many of you have actually worked with information theoretic approaches to higher order interactions. I know that, if you work with like, Giovanni, there's a lot of topological data analysis kinds of approaches, but I'm taking a very information based approach. And then I'm going to use present a case study, which is analysis of fMRI data. As we just mentioned, my background is in neuroscience, and so that's the data that I typically reach for when I'm trying to study some feature of multipartite interactions in a complex system. But I want to say that this is not a neuroscience talk. Everything that I'm talking about is general, and so if you have other data that you're interested in, climate data, disease spread data, it doesn't even have to be time series data if you don't want to. That is also sort of on the table here. And I'd be happy to talk with you guys afterwards about where else dark information might be relevant in the study of systems generally. And then I'll sort of wrap it up by sort of looking forward and what this means for my research program going forward and what I hope this means for the future of complex systems research and information theoretic applications therein. Okay. So um, when I talk about dark information, what do I mean? Okay. And so when I talk about dark information, I'm really making an analogy to this idea of dark matter. Okay. I'm not a cosmologist. I have no background in physics. Maybe some of you do. And so just sit on your hands if I'm, playing a little fast and loose with some of the space science here. But we have this idea in cosmology of dark matter. Okay. And dark matter forms the vast majority of the stuff, and note the scare quotes, stuff in the physical universe. We know that it's there, but we don't really have great technological or theoretical frameworks to really interact with it. Okay, it doesn't fit well into the existing, very successful models, that you do see in physics. So it's out there, there's a lot of it, but you know, our science just really isn't currently up to the task of really grappling with it to the extent that we would like to be able to. And so when I talk about dark information, I'm talking about something very similar. It's this idea that there is information out there that potentially forms the vast majority of the structure, quote unquote, in complex systems. And I'll be talking about the brain, but again, this is not brain specific in any way. Um, and that we don't currently have many tools to sort of directly observe it or interact with it. And it doesn't fit very well within the existing approaches to modeling complex systems that you see in neuroscience, that you see in biology. Things like networks, things like manifold learning. And so, I don't want to stretch this analogy farther than is strictly appropriate, but my hope is that by casting this idea of dark information in analogy with dark matter, I can kind of communicate this idea that, this is a big puzzle, right? This isn't just some mathematical shell game that I'm playing, around the edges, but I think there's actually something very deep happening here. And so, when I talk about dark information, like, can I formally define this idea? Okay. And yeah, I'm going to say that dark information is higher order, you all know what that means, but specifically synergistic higher order information that is present in multiple elements of a complex system and not learnable from any simpler combination of parts. Okay. And these are the two papers that came out of my PhD. And I'll be going through some of this stuff in a little bit more detail. I can't really see, a show of hands, but if I say, synergistic, does that mean anything to folks here? Just to put up your little hand on the Zoom emoji. Okay, yes, Cyril. Yeah. Okay. So to really make this idea of synergistic information rigorous, we're going to have to do a little bit of catch up here, talking about information theory and its applications to complex systems. Okay. So I'm sure most of you, especially those of you who have backgrounds with physics, are familiar with sort of the basic idea of entropy, right? It's this, people get this tattooed, negative sum of p log p. Okay. And the idea is that for a random variable x, which could be multivariate, which takes states from, a support set according to a probability distribution P. This value, negative sum of P log P, is equivalent to the amount of uncertainty that you have as an observer about the state of variable X. Okay, and so there are two equivalent interpretations of this, right? There's how many yes or no questions on average do I have to ask to uniquely specify the state of our random variable? So, if I roll a dice, I can ask, is it an odd number? Is it an odd number? Yes. Is it greater than three? Yes, and so on. Um, that's one way you can think about entropy. The number of yes/no questions you'd have to ask to specify that the dice is actually in five. Okay. Or there is this more general interpretation of, on average, how uncertain am I about the state of the variable, right? If I roll a fair dice, I'm somehow more uncertain about what number came up, is likely to come up than if I know that the dice is rigged and it, rolls a two, two-thirds of the time. Okay? And what's really important here is that entropy is about your beliefs as an observer. Okay, we like to think about entropy as a sort of an innate quality, something that exists out in the universe like mass or velocity. But I actually think that entropy is much more about the models that you build as an observer. The entropy of a dice does not really exist in any meaningful way outside of your head. And I know people might object to that, but I'm something of a strict Bayesian, theologically speaking. And so when I'm talking about information here, what I really mean is I'm talking about your beliefs as an observer. And then so if we have two variables, let's say we've got, x1 and x2, we can quantify the amount of information that they share just by asking, okay, well, how uncertain am I about the state of x1, initially? What are my initial beliefs about x1? And then I'll subtract off the uncertainty about x1 that remains after I have learned the state of x2. Okay, this is, a very straightforward sort of example of like an intersection kind of function, right? Um, the difference between these, my prior uncertainty before I learned the state of x2 and my posterior uncertainty after I have learned the state of x2, well, that's the amount of uncertainty about x1 that is resolved by learning x2. Okay, it's the uncertainty that, it's the questions that I basically get answered for free, right? I had to ask some number of yes/no questions to specify x1. If I observe x2, then, some of those questions, are just, already answered, essentially. Okay. And so this difference is the mutual information. It's the uncertainty resolved about one variable after you learn the other. And importantly, If x1 and x2 are independent, then the mutual information is 0 bits. Okay, so it really is a direct measure of what you might call correlation between these two things. And, very conveniently, it is symmetric in the arguments. So it doesn't matter, whether my prior is x1 or x2, the mutual information works out to be the same. Okay. Um, and this is where, like, in my experience, 99% of, complex systems analyses, particularly in neuroscience, stop. Okay. Um, a typical pipeline, in my field might be, you observe your favorite system, in my case, the brain. You parcellate it into components. That could be neurons, that could be regions of the cortex, that could be whatever you want. You extract some data from each parcel, and then you compute, some correlation or some mutual information between them. Okay. And then you call that, that looks like a adjacency matrix, and Bob's your uncle. You can go off and do all of your favorite network analyses, community detection, modularity, whatever you want. Okay. Um, and what I'm going to argue here is that, while this does always work in the sense that, like, you can do it, you can make a network out of a covariance matrix, you're missing really, really important information. Okay. Uh, and so, to sort of build some intuition here, I want you to imagine that you're a scientist that is just observing this system. Okay, this is a system that just draws, three binary elements. That every time you observe it, it's drawing a state at random from some unknown probability distribution. Okay, uh, you look at it. All three variables are in a state. You look at it again, they're in some new state. Okay, and you just like collect data on this thing, for some large number of times, and you try to build a model of the system. Okay. And just out of curiosity, you can shout it out. Does anybody recognize this system? Just like looking at the yellow and black dots. I've done this example a couple of times, and I'm always curious to see if people know it. Um, going once, going twice. Okay, all right, we'll get there. So you're a scientist, you've observed the system, you've collected some data, and you get this probability distribution. Okay, you say, well, about a quarter of the time they're all off, and about a quarter of the time, one is off, two is on, and three is on. Okay, and this is your very, very simple model of the system. Anybody recognize it now? This is a little bit more obvious what we're looking at. Yeah. Okay. Um, but let's pretend we're not computer scientists. We don't know what this is. How would we model this system? Okay. Um, if you are trained in complex systems like I am, your first instinct might be to say, well, let's do a network. Let's compute a set of pairwise correlations between every xi and xj, and that'll be our functional connectivity network of the system. We'll publish a bunch of papers in network neuroscience, and it'll be great. Okay. Um, the problem is that if you try to compute the pairwise correlations between any one of these elements, they're all 0 bits, okay? No element is correlated with any other element, right? There's no structure there does not appear, I should say, there's not appear to be any structure in this system at all, okay? Um, and so you might just say, well, maybe they're all uncorrelated. Maybe this isn't a system at all. It's just a kind of ideal gas of, white and black dots turning on and off. And, there's no point trying to model it as a system. But if you actually compare our observed distribution, these four possible global states, with a truly random distribution, this is what you would get if you had, three binary states, each one independent of every other. These are clearly different distributions, right? And if you compute something called the Kullback-Leibler divergence of our true observed distribution from this, random maximum entry distribution, you'll find 1 bit of information in there, right? That's 1 bit of deviation from independence. And so we have this sort of puzzle where we have a system that has no pairwise interactions between any elements, but there is 1 bit of information like somewhere in there. Okay. So where is it? And the answer is that, because this is a logical exclusive OR gate, um, the only way you can see the interaction is if you go higher order. Okay, there's no way you can model the system as a network, but if you now allow for multivariate dependencies, suddenly you get 1 bit of information almost from nowhere, right? So while the pairwise mutual informations are all 1 bit, are all 0 bits, the joint mutual information of x1 and x2 onto x3 is 1 bit, similar to x1 and x3 onto x2, yada, yada, yada. Okay. So if you know the state of any pair of elements, you automatically know the state of the whole system for free. But knowing any single element alone does not give you any information about the state of any other element. Okay. And so when I talk about synergy, this is what I mean. Okay. This is information that is in the joint state of all the elements that is not learnable when you consider just the pairs. And so to move forward with this, we really need a formal logic that can describe these interactions between three or more elements without reducing them to combinations of lower order elements. Remember, you can't just cast this thing as a network and try to obliquely infer, the global properties from some combination of pairwise properties because there are no pairwise interactions. It's only information present in the whole. Okay? And so this formal logic is really, what we use, what we're trying to develop when we talk about multivariate information theory. Okay? And so um, I know I said save questions for the end, but before we jump into the really the more complicated stuff, does anybody have any like technical questions about anything I've just presented? Conceptual stuff saved for the end, but like everybody understands like the gist of what I've said so far. You can just take 2 minutes if anybody has any questions about that. Specific questions. Okay, going once, going twice, gone. Okay, so multivariate information theory. So the idea behind multivariate information theory is we want to look at the interactions, that can happen between three or more elements, right? We don't want to restrict ourselves just to the case of, bivariate mutual information, all right? The problem is that, once you allow for three or more elements, you immediately hit a really weird conceptual wall, which is that if you have three or more elements, there are actually multiple kinds of correlation that can coexist. Okay. If you're only used to thinking about mutual information or like the Pearson correlation, it's kind of weird to think about like what does it mean different kinds of correlation. Okay. But if you are in, the higher order information space, what you can find is you can find redundant correlations. So that is information that could be learned by observing X1 alone or X2 alone or yada, 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 XN alone. All right. And so you can kind of think of that as being sort of related to ideas of synchrony, right? If you know the state of any one synchronized element, you automatically know the state of all the others. It doesn't matter which one you observe, they're all synchronized. In contrast, synergy is information that can only be learned when you observe X1 and X2 and yada 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 and Xn all together, right? So it's like the example of the XOR gate I gave in the last example, right? If you try to observe any one on its own, you get nothing. You can only get learnable information out when you observe X1 and X2 together. All right. And so this doesn't happen in like the pairwise world of like Pearson correlations, right? This is something that only happens when you go higher order. And what's even worse is that these two things can coexist, right? You can get odd combinations of redundancy and synergy, such as the information that you could learn by observing X1 and X2, or X1 and X3, or X2 and X3. And as you can imagine, sort of as the number of X's gets big, the number of possible combinations of ors and ands balloons really alarmingly. Okay. And so even just like going from two variables to three variables means that, the world has become a lot more complicated and computationally a lot more intensive. Okay. And so I kind of went through these examples a little bit, but when we talk about redundancy, just to build intuition, I really like this figure. I think these are soldiers from North Korea, marching through Pyongyang, and they're all in like perfect lockstep, right? And so if I tell you, okay, what's the angle between the legs of, one soldier, you automatically know the angle between the legs of all of the other soldiers because they're all doing this goose step together, right? It doesn't matter which one you look at, you automatically know the state of all of the others. Okay, so typically we associate redundancy with synchrony, right? It's the same motif repeated many, many, many times. Okay. Synergy is a lot harder to kind of understand beyond saying that it's kind of like an XOR gate, which really is not helpful when you're considering a continuous real valued system. My go-to example is something like a symphony. Every instrument in a symphony is playing a slightly different piece of music, right? The strings are not playing the same thing as the drums are not playing the same thing as the horns, but somehow all of those things interacting together creates an experience that is richer or more interesting, perhaps, than if you were just listening to the strings on their own, or just listening to the drums on their own. Okay. It is structure that is in some sense greater than the sum of its parts. And so if you're like me and interested in questions about emergence or um, you know, consciousness or whatever, this really has sort of an interesting flavor to it. And so, coming back to the dark information hypothesis, is that we can sort of take this idea and make it a little bit more formal and say specifically that almost all the most popular tools in complex systems are sort of preferentially sensitive to redundant interactions and are functionally blind to these synergistic interactions. Okay. And so when I talk about dark information, that is sort of not visible, what I'm really talking about is this bias towards or bias away from being able to directly perceive synergistic interactions. Okay. And so this is not my example, but I heard this at the Santa Fe Institute a couple of months ago. Somebody said that, existing tools, like correlation, all they can really ask is, is everybody jumping at the same time, right? Like, is everybody just like all the dancers, just like jumping up and down at the same time? But what we really want to know is, are they dancing, right? Are they moving in different ways that are somehow more interesting, more collectively organized than, you know, just are they all jumping at the same time? So that's really what I want to do. I want to develop, a mathematics that can tell us, when systems are dancing and not just are they all jumping. Okay. And so we need mathematical tools to do this. Okay. It's nice just to use, fancy intuition pumps like symphonies and ballerinas. But, we would like to make this formal and rigorous. Okay. And so there is a small but growing literature on quantifying these higher order interactions. And I won't go through all of these, but I'm happy to send these slides around to whoever wants them. All of these are different approaches that have been developed in the last 10 years. Some are based on decompositions, some are based on um, stochastic random variables. Some of them are based on sort of extensions of mutual information. And there's a growing group of people that have been proposing these, and you'll find different papers applying them in different contexts. Okay. I'm going to look specifically at this last one here, extensions of multivariate mutual information. One, because they're really useful when you're dealing with continuous systems. They're nice Gaussian parametric estimators, and also they're the easiest to explain in a short period of time. Things like the generalized information decomposition require a little bit more background than I have time to go through now. So earlier I introduced this idea of the bivariate mutual information, okay, which quantifies the degree to which knowing the state of x1 reduces our uncertainty about the state of x2. Okay, you can generalize that to a measure called the total correlation. Okay, and the total correlation is the difference between the sum of all the marginal mutual informations and the joint. If you're familiar with something like a Kullback-Leibler divergence, it's equivalent to the divergence of the true probability distribution from the product of the marginals. In the interest of time, which I'm trying to keep an eye on, I won't go through this in any more detail, other than just to say that you can think of this as a measure of how different is your system from an ideal gas, right? If every xi is independent from the rest of the system, then the total correlation is going to be 0 bits, right? The larger this value, the more your system globally deviates from independence, the less like an ideal gas it is. Okay? Unfortunately, this will not disambiguate between, these notions of redundant higher order interactions and synergistic higher order interactions. And so for that, we need something called the O information, okay, which was first proposed by some friends and colleagues of mine, Fernando Rosas and Pedro Mediano and others. And you can think of it as a summary statistic that measures specifically the higher order deviation from independence. Okay. And so it has this kind of peculiar form. You could think of this as sort of a whole minus sum kind of measure. So you start with the total correlation of the whole system. Okay. And then you're going to multiply this some large number of times, right? Specifically n minus 2 times, where n is the number of elements you have in your system. Then you were going to subtract off the total correlation of all the subsets of size n minus 1, right? So if you have, three variables, x1, x2, x3, this is going to be the total correlation of x1 and x2 plus the total correlation of x1 and x3 plus the total correlation of x2 and x3, okay? This little minus I superscript says the joint state of every element excluding the ith one. Okay. So you have the whole, you subtract off the sum of its parts, and then for sort of historical reasons of historical accident, you slap a negative sign on this. I can explain why later, but for now, it's just something that you've got to do. And so the interpretation is that if this measure omega is greater than zero, then the system is redundancy dominated. Okay? So if this thing is positive, your system is more like the marching North Koreans than it is like the symphony. Okay, and I realize that is very vague. You're more like marching North Koreans than you are like a symphony. This is more of an intuition pump than it is a rigorous derivation because I don't have time for the full derivation. In contrast, if the O information is negative, then your system is synergy dominated. It is more like the symphony than it is like the marching soldiers. And of course, if all the elements are independent of each other, then the O information is 0 bits. Okay? So what that tells you is that a non-zero O information, whether it's negative or positive, is sufficient to show that X has higher order structure and that higher order structure deviates from independence, okay? It is not necessary, but it is sufficient to show that a higher order interaction exists, and the sign of the O information will tell you whether that interaction is redundancy dominated or synergy dominated. Okay. Um, and so, we've built all of this, intuition up. We've built some mathematical measures. We've got our O information. And then so, you might ask, and I get asked this all the time, is does any of this actually matter to real scientists, right? Does a neuroscientist, trying to cure Alzheimer's, do they care about this? Or is this just like kind of a mathematical shell game you can play because you think XOR gates are neat? And I do think XOR gates are neat, but I'm going to next sort of walk you through a case study that I think argues that we do need to be taking these interactions a little bit more seriously and investing more in these tools. Okay. Um, and so this brings us to the analysis of the fMRI data. I am a little ahead of schedule, actually. So we'll have plenty of time for questions at the end. And so, if you're not a neuroscientist, you can kind of just, zone out or whatever for the technical details coming up. But this is one subject taken from the Human Connectome Project. There are 4,400 frames. If you're a neuroscientist, you call these TRs. If you're a statistician, you might call these samples. But it just means that, we've taken a video of the brain for some period of time, and we're going to treat each frame of that video as if it is an independent draw from some multivariate normal distribution. We've taken the cortex and we've parcellated it into 200 brain regions, which is pretty standard in the field. And I've computed the O information and a bunch of other measures for all sets of three brain regions. And I'm going to talk mostly about the O information for now, not the total correlation or the pairwise mutual information. And then in addition to computing the total correlation for all the triads, I'm going to compare the higher order information measures to two very common pipelines used in complex systems. Okay, one is the network analysis, and I'm going to talk specifically about functional connectivity networks. And the other one I'm going to talk about is a PCA-based manifold learning analysis. Okay, and I'm going to specifically look at how much variance is explained by the first principal component. Okay, a very common analysis when or pre-processing step when you're analyzing high dimensional data is to pump it through some kind of PCA and say, aha, well, we'll figure out how much variance is in the first, X principal components, and we'll just operate on those, try to get that dimensionality down a little bit to something more manageable. And what I'm going to argue, and hopefully convince you, is that both of these things, both of these measures, both these approaches, I should say, the network analysis and the manifold learning analysis, really struggle to appropriately represent, specifically higher order synergistic information. Okay, so we've got the network, we've got the principal component, and we've got about 1.4 million sets of three different brain regions, which I've computed O information for all of them. Okay. And so let's start at the functional connectivity network. Okay, there's a lot happening in this, so we'll take some time going through it. So, I started with the pairwise mutual information. Okay, so this is just the mutual information between every pair of brain regions. Okay, and then I used a multi-resolution consensus clustering algorithm to group these into modules. I'm sure all of us are sort of familiar with the basic idea of community detection and its application to networks. Okay, so we get this very nice looking thing. You could slap this on the cover of Network Neuroscience, and we all love a good adjacency matrix. I then looked at the structure of these sets of three brain regions as a function of whether they are one, redundancy or synergy dominated, and two, how they fit into sort of this network map. Okay, so let's look at these CDF plots over here. Okay, if I look at the redundancy dominated triads, the triads that sit the of the triads that are redundancy dominated, okay, about 52% of them sit within one community, okay? And they have the highest normalized O information. Remember, the higher the O information, the more non-negative it is, the more redundant it is. Okay, so this kind of makes sense because we're looking at redundant triads. Okay. And so that means that triads that all sit within one community, say this upper square, this is where you'll find most of the redundant triads. They are also, of the redundant triads, they have the strongest positive O information, and most of the redundant triads are all within one of these communities. Okay. If you look at triads that sit within two communities, so that's this sort of middle curve here, that's about 45% of redundancy dominated triads. And then finally, almost no redundancy dominated triads sit within three communities. So if you have, a set of three nodes, the first is in community one, the second is in community two, the third is in community three, you will almost never find that that is a redundancy dominated triad. Okay, it just doesn't happen. And, the normalized O information is the weakest one, right? This is technically negative, but this has more to do with like the estimators. For our purposes, it is still considered redundancy dominated. Okay. In contrast, if you look at synergy dominated triads, okay, notice that, we've got a lot more negative down here. Um, Almost no synergy dominated triads sit within one community, right? Like less than 1%. And you can see that this CDF plot is extremely rough. This just never happens. In contrast, 51% of the synergy dominated triads all sit within span three different communities. Okay, these are the most negative. This is the most of them, and they have the strongest sort of smoothest curve here. And so what this tells us is that if you do a community detection based approach, what you're really seeing is you're really seeing redundant interactions. Okay. There are synergistic interactions. There are lots of sets of three brain regions that have synergy, but there's sort of split between the three different communities. They're sort of in the hollow spaces between the different communities. The community detection creates a map of the system that is just very unnatural for representing synergistic interactions. Okay, because the community detection tries to say, okay, well, these are the functional modules, right? These are the internally coherent pieces. But they're really not referring to a particular kind of they're failing to represent a particular kind of coherence, right? Which is the synergistic deviation from independence. Um, that's just parcellated off across the nodes in a way that is very alien to the functional connectivity modularity maximization structure. Okay. And then if we also just look at the values of the pairwise mutual information, so for the redundant triads, the average pairwise mutual information is much higher than the average pairwise mutual information among synergistic triads, right? If you were just to look at a synergistic triad and model it as a network, you would see three very weak pairwise dependencies between them, and you might just assume that they're largely independent, right? You'd say, okay, well, there's, three weak edges. They're just not very well integrated, right? But that's not true. They could be extremely well integrated. They're just well integrated synergistically, which the functional connectivity network based on pairwise mutual informations cannot fully represent. Okay? The same thing happens if we look at the principal component analysis. Okay, so again, on the x-axis, I'm using slightly different notation because this is from a different paper. But we have again, this normalized O information. And then on the y-axis, we have the variance explained by the first principal component. Okay. And again, I've looked at all of the pairwise, or all of the triples in the sets of three brain regions in the system and split them apart by whether they are redundancy dominated or synergy dominated. Okay. And so the first thing you notice, really strong positive correlations, right? The higher the normalized O information, regardless of whether you're redundancy or synergy dominated, the more variance is explained by the first principal component, right? And so for the very redundant triads, these ones that have a positive O information, like up of, zero point 0.1, zero point 1, 0.5, that's explaining like, 95% of all of the variance, right? The redundant C-dominated triads are extremely compressible, right? You only need one principal component to capture, 95% of the variance, okay? And the more redundant the system is, the more compressible it is. Similarly for the synergy dominated triads, again, the more sort of redundant it is, synergy dominated, but not as synergy dominated, the more compressible it is. But then also, if you look down here at the most synergistic triads, these have almost equal variance explained on the first, second, and third principal components, right? Remember that if you just have white noise, well, the variance explained by the first principal component will be 33%, and then the second principal component will be 33%, and the third principal component will be 33%. These are not white noise, right? Again, these have strongly negative O information. They are strongly deviating from independence and have real higher order interactions. But the principal component analysis thinks that you have, equal variance or about equal variance on each component, right? It can't distinguish between the white noise case and this synergy case. Okay, so just like with the functional connectivity networks, you could look at this triad and you could say, hey, that looks pretty much like three independent uncoupled elements, but actually they're not independent and uncoupled. They're highly integrated. They're just synergistically integrated as opposed to redundantly integrated or pairwise integrated. Okay, the only way that you can actually see that these things are deviating from independence is with the O information, with this measure that sort of allows for synergistic interactions to become visible. And then again, this is just sort of the same plot as above. We look at the synergistic triads and redundant triads, proportion of variance explained, significantly different. The redundant triads are much, much more compressible than the synergistic triads, and some of the synergistic triads look like white noise, from the perspective of the principal component analysis. And so, again, this is just a case study. This is just looking at, one way of processing fMRI data. But I think that this points to some really interesting failure modes for these two really, really popular ways of analyzing multivariate data, right? The functional network fails to capture synergistic structure because the communities, which is our go-to analysis almost all the time, specifically reflects redundantly integrated sets of nodes and is blind to synergistically integrated nodes, right? And those synergy dominated triads kind of sit between communities and what I like to think of as like hollow spaces in the functional connectivity network. And, if you look at the pieces that the network is built off of, the pairwise mutual information or the pairwise Pearson correlation, those pairwise measures specifically correlate with redundancy and not synergy. And I should say there are also math reasons why this has to be the case. I didn't have time to include them in this talk, but this is not totally surprising if you were to actually take like a more formal, like decomposition-based approach, and I can talk about that afterwards as well. Um, but there's also a whole formal argument to be made here that I'm not going to make here. And then similarly, manifolds, or at least manifolds based on principal components, also fail to capture synergistic structure. Okay, the triads where one principal component explains most of the variance are overwhelmingly redundancy dominated, right? Because redundancy means compressibility, right? And in contrast, triads with a very high degree of synergy will appear random, right? Variance is equally distributed over all the components in a way that looks a lot like what you would expect to see in the case of white noise. It's just that they're not random. They're just integrated in a way that the principal component analysis is unable to see. And so, as we kind of come to the last, let's say, 10 minutes or so of the talk, I want to look forward and say, what does this mean for us as, students of complex systems and, for those of us particularly interested in higher order interactions? Okay. Um, One question that you might ask is, does synergistic information even matter, right? Okay, well, maybe it's there, but, who gives a crap? Okay. Um, This is a really good question, and I don't think we have a great answer to it yet. But there is some really interesting work that's been coming out, some of my work, and then some collaborators of mine in the United Kingdom, specifically shout out to Andrea Lupi and Fernando Rosas and Pedro Mediano, who have started to show that synergistic information does seem to be correlated with things, at least in neuroscience, that we are interested in. Okay, so synergistic information is decreased when consciousness is lost, either via anesthesia or traumatic brain injury. And, remember that synergistic information is sort of has this greater than the sum of its parts, emergent kind of flavor, which, makes the link to, consciousness quite interesting. Similarly, I just published a paper like a week ago showing that the amount of synergy in the infant brain predicts later cognitive development. So if you look at an infant and how much synergy is in their brain you know, right after birth, that will predict how well they do on cognitive tasks like 2 years later. So there's, some predictive power in there as well. We have reason to believe that psychedelics change the balance of redundant and synergistic information in neural cultures, and then also more recently in whole large-scale brain imaging. And then for those of you who are interested in artificial neural networks, there's some pretty cool work suggesting that synergy facilitates multimodal processing in artificial neural networks. So it's not just performance, but specifically for neural networks that have to integrate information from multiple modalities or have to solve different kinds of problems simultaneously. Synergistic interactions really facilitate that. So we're a long way from a grand unified theory of synergy in complex systems, but I think there is enough here to suggest that this is worth investing in, right? And this is worth putting in the cognitive effort. And then so to bring it all back to this idea of dark information, at the very, very start, I said, one of the defining features of dark matter is that we know that it, seems to make up the vast majority of the stuff in the universe, right? It's, I don't have an actual estimate, but it's something like, more than 90% of all the mass in the universe is thought to be dark matter. Okay. Um, and again, with the dark information analogy, if you just think about the combinatorics of higher order interactions, there are way, way more possible higher order or dark dependencies that might exist than there are pairwise dependencies, right? So if you have a directed graph, right, there are going to be n squared minus n possible directed dependencies, right? Um, but if you look at third order, fourth order, fifth order, as the order interaction increases, the number of possible dependencies increases approximately with the I'm totally drawing a blank. This is the binomial coefficient, I believe. N choose k possible interactions, right? So if you have 200 brain regions, which is like standard for neuroscience, there are about 20,000 possible edges, right? But there are, what is this number? 2.5 billion possible sets of five brain regions, and just like so many sets of 10 brain regions that I don't even know what that number is, 10 to the 16. Okay. So we've really only scratched the surface of the possible space of interactions within like even a really coarse model of the brain, right? Just 200 brain regions. Forget about the fact that there are, millions of neurons and billions of synapses in the brain itself. Okay. So we've really just only scratched the surface here. Okay. And so I don't know if all of these interactions contain meaningful information. Maybe they do, maybe they don't. But the size of the space is really remarkable. And so synergistic or dark information really could, account for a vast amount or vast majority of the space of possible interactions in a system in a way similar that, to the way dark matter makes up mass in the universe. And so if here at the end, you'll sort of permit me to get a little bit romantic, I sometimes feel like, we're sort of on like a beach, with our networks and, our little, maybe we do look at th sets of three or three brain regions or whatever, we're kind of just splashing around in the shallows, but there's like this whole ocean, this like mind-bogglingly vast ocean. And then beyond that, like a whole cosmos of possible interactions in complex systems that we have never even begun to explore because up until now we've never had anything like the kinds of tools required to even know that it's out there, right? Like we've only just gotten a look at the horizon now, forget about actually setting sail and going out looking to see what's out there. So if anybody wants to give me a tenure track professorship, this is what I'm going to spend my career doing, is trying to get out beyond the shallows and see what's out there in this space of higher order interactions. Thank you to first the team from Indiana University that helped me during my PhD. So that's Dr. Olaf Sporns, the newly minted Dr. Maria Pope, Dr. Josh Vaskowitz, Dr. Maria Grazia Pukshadu, Dr. John Biggs, and then my current supervisor and team at the Vermont Complex Systems Institute, specifically Dr. Josh Bongard here on the right. I'm at the Institute. I was part of the CNSNRT at Indiana University. And then I should also shout out the Cold Regions Research Engineering Laboratory, which is the branch of the Army research that cuts my paychecks and makes sure that I can like buy food and pay rent and everything. So I think that's what I've got. We want to open the floor to questions.
Thank you very much. It was a very interesting talk. And yeah, if anyone has any questions, feel free to ask them. Either turn on your mics or you can ask them in the chat and I'll do the question.
Uh, can you hear me?
Yes, I can.
So yeah, my laptop cannot recognize the microphone, so I am video camera on the laptop and microphone on the phone. I hope it works like this. Yeah, thanks so much for the talk. I'm very interested in working more also with information metrics, specifically like multivariate information metrics, and yeah, detecting these high order interactions. Um, So I want to focus on self-organization and criticality. And I was wondering if you think it's possible to use these information metrics to as a sort of order parameters to detect some kind of phase transition, something like that.
Yes. I was working for a little while. Kind of project sort of fell off as the United States is falling apart. But I was for a little while, I was working with a guy named Demian Cho, and I would encourage you to check him out. Um, Sort of on exactly that question, what happens to, a network of spiking neurons as it transitions from, subcritical to supercritical? And one of the things that we saw was that, yeah, it does seem like synergy peaks at least around the critical point. I don't necessarily know if it is like a perfect order parameter, that diverges right at criticality, or if it's maybe more like an early warning transition. I think project kind of fizzled before we got there yet. I believe Daniele Marinazzo had a paper years ago suggesting that synergy was an early warning sign of an oncoming phase transition. That was just like in an Ising model. Um, However, one of the things that always sort of sits in the back of my mind is that maybe yes, synergy peaks near or around the critical point, but is it possible that's just kind of trivial, right? Because if you think about a system that is like, totally supercritical, right? It's like crystallized. Well, then that's going to be totally redundant, right? Like it's going to be, like an Ising model where all of the spins are perfectly in sync, right? And then if you have a system that's just totally disintegrated, everything is just random, well, then there's no higher order structure possible there either, right? It seems like synergy kind of has to exist at least around the critical point because it can't exist on either extreme, right? Either everything is synchronized because the system is crystallized, or there's just no structure at all because the system is like an ideal gas. And so if it can't be on either extreme, well, then it sort of has to be in the middle, right? And so whether that's like deep or trivial, I think you could probably argue either way. But I would be very interested to see, what results come out of your research, either way, right?
Yeah, I see. Okay, thank you. I mean, I had one more simple question, so to say. We were talking yesterday and today also a bit about estimating. Oh, sorry, about estimating the entropy. So I was wondering how you estimate the entropy for continuous distributions.
Yeah, so that's a really hard question. And I would encourage you to check out some of the work by Joe Lizier. That's Lizier. He's in Australia. I think he's at Sydney. He has written, particularly the paper for the JIDT toolbox has a good tutorial on information estimators. There are sort of two approaches you can make for continuous random variables. Okay. If you are willing to make parametric assumptions that your system is Gaussian, then you can compute the entropy directly from the definition of a multivariate Gaussian distribution, right? That has a closed form for a probability of X. It's some exponential thing or whatever, and you just slap a negative log on that. Okay. And that is a that's a perfectly fine Gaussian estimator. Can you hear me?
Yes, we can. I don't
Okay.
know exactly what was the point. Cyril, I think your mic is off.
Ah, sorry. Yeah, you
Yeah,
were
now it's
talking
fine, right?
about the entropy estimation for continuous distributions if it's non-Gaussian.
Yes, so yeah, if it's Gaussian, you can do there's a closed form estimator. If it's not Gaussian, you can use what's something called a Kozachenko-Leonenko estimator. And this is also discussed in more detail in some of Joe Lizier's writing, and also I wrote a tutorial on information theory for complex system scientists, what I can send around. The idea is that you can use a k nearest neighbors graph to estimate, the local probability of a given point based on how close it is to other points in the cloud. And from that, you can sort of bootstrap measures of mutual information, O information, etc. Uh, they're very data intensive. If you have millions of points, that's a very big k nearest neighbors graph, right? And so, you'll have to do a little bit of thinking about whether you want, to make simplifying assumptions, which could be incorrect in the case of nonlinear systems, but are easy to compute, versus if you're willing to take on the extra computational burden of inferring a big k nearest neighbor graph. Yeah, but those are the two that I would look at. There's the Gaussian estimator and the Kozachenko-Leonenko estimator.
Yeah, yeah. All right, thank you. Yeah, I have one more question, but maybe somebody first. I don't think we have that much time. Thanks a lot.
Any more questions from the audience? I think maybe you can ask the third question, Cyril.
Yeah, lastly, I was wondering if you somehow quantify the synergy or redundancy, or how you distinct between if an interaction is purely synergy or redundancy, because this all information, for example, the sign gives the dominance of the yeah, redundant or synergy, but you don't know if they are maybe very high in both redundant and synergy, but synergy is more dominated. So I was wondering, especially in the one of the last talks where you show yeah, the relevance of synergy and redundancy.
Yeah, so that's a very hard question, and I don't think the field has a sort of a, an agreed upon answer right now. If you have a small number of variables, you could do the full partial information decomposition, or one of its generalizations, like the generalized information decomposition. That requires you to make some ad hoc decisions about how you define redundancy. Different partial information decompositions, different redundancy functions can give you different partial information decompositions. So, you've kind of got to make a choice as to what your working definitions are. And also, if you have more than about four elements, the PID is uncomputable. So, that's not great. Um, One thing you could look at is, so the O information, I presented it as the difference between, two total correlations, the total correlation of the whole minus the leave one out marginals. But you can also compute it as the difference between the total correlation minus another measure called the dual total correlation. And if dual total correlation is greater than total correlation, O information is negative. And so I've seen some people say that you can kind of use total correlation as a heuristic measure for redundancy and dual total correlation as a heuristic measure for synergy. Like, mathematically speaking, that's not totally valid, but again, if you don't actually need like the exact perfect amount of synergy, baked in by God, and are really just interested in looking at like relative balances, that would be probably what I would do, compare the DTC and the TC. Um, then the last thing that I might suggest would be maybe looking at like null models. You might be able to build something where it's like, okay, we're going to try to preserve, we'll build a null model that, preserves the first order pairwise interactions, but disrupts anything of order three or greater with the thought that like, maybe that could disrupt the synergies more than the redundancies because the redundancies are kind of represented by those pairwise interactions. That one is a little bit dicier, but I think a lot depends on specifically what your data looks like, how many elements you're looking at specifically, what kind of compromises you're willing to make, and how sort of experimental you're willing to be, in terms of what exactly your analysis is. But yeah, it's a hard question that I don't think anybody has a perfect answer to just yet.
Building up on that question, I wanted just to clarify that if we have, for example, a more negative O information, it means that synergy dominates more than redundancy, or
Yes.
is it just a binary, is it a binary question in terms of negative or positive?
No, so it's all about dominance, right?
The
You could
absolute
have
value matters.
yes. So a system with a negative O information could still have a lot of redundancy. It's just it has more synergy. And so that's kind of the problem that Cyril is referencing is that it's
Because then,
very hard to know to specifically tease the two kinds of interaction apart.
okay. Are there any other questions from the audience? If no, then I would like to thank the speaker again
Okay.
for the availability, and I hope that I will see you again in future Beyond the Edge seminars.
Yeah, absolutely. Thank you guys for inviting me. And I'm sure you can get my email, from one of the organizers. If you have any other questions or want to collaborate or anything, just, feel free to hit me up and I'm happy to talk shop with anybody who's interested in this stuff. Yeah.
A lot.
You guys.
Bye, everyone.